Hello viewers, in today's lecture we are going to discuss two very important problems from homogeneous differential equations, right? So in this session we are going to solve these two important differential equations which are homogeneous differential equations, right? And we'll also see that how we can convert or prove that these two differential equations belongs to the set of homogeneous differential equations, right? So let us start. So viewers, we have already discussed these type of differential equations in our earlier lectures, but here just for the sake of beginners, we are going to solve these two differential equations, right? So here in the first equation we have the equation xy dy plus y square minus x square dx is equal to 0, and here we are also given the boundary condition, that is when x is 1, y is 1. In the second equation, we have xy dx minus x square plus 2y square dy is equal to 0. And the boundary condition is when x is 0, the value of y is e. So now let us first take this equation. So here we have xy dy plus y square minus x square dx is equal to 0. And now we can first express this differential equation like this, that is xy is equal to xy dy dx is equal to negative of y square minus x square dx. So taking this term to the right hand side, so now we can write xy dy, and here we can now reverse the two terms. So we have x square minus y square, and here we have dx. Now let us separate the terms here. We can take dy over dx, and here we have x square minus y square over xy. So the first step to get an expression for dy over dx, right? And later on we'll see that in the second equation we have to form an expression for dx over dy, right? So we are here discussing two types of homogeneous differential equation, that is type 1 and type 2, right? So here we have dy over dx is equal to x square minus y square over xy. And now we can see that here the numerator and denominator both have degree 2, right? So here the degree of the numerator is 2 and the degree of the denominator is 2, because here we have 1 and here we have 1. So this is 1 plus 1, 2. So here let us take this right hand expression as some function, say f of xy, right? So this is x square minus y square over xy, and let us replace x by lambda x and y by lambda y, right? So what we will get, we'll have f of lambda x comma lambda y, and here we have for x we have lambda x square, and here we have lambda y square, and here we have lambda x times lambda y. So we can now write lambda square x square minus lambda square y square, and here we have lambda square xy, and we can now easily see that we can cancel out lambda square from the numerator and denominator. So we are left with x square minus y square over xy, which is the same expression, right? So we can now write here f of x comma y. So whenever in a function we replace x by lambda x and y by lambda y, and we form a function, new function f of lambda x comma lambda y, and if this function is equal to the original function, that is f of x comma y, then we can say that this function is a homogeneous function. So here we can also write f of lambda x comma lambda y is equal to lambda raised to 0. And because here we can write f of x comma y as lambda raised to 0, because lambda raised to 0 is simply 1, right? So we have f of x comma y, right? So here we have seen that this function is a homogeneous function of degree 0. So now let us take this function in another way, right? So what we will do, we'll take x square common from the numerator. We have 1 minus y square over x square, and here we have xy. We can cancel this x. Then we have x 1 minus y square over x square, and here we have y, right? Now taking this x to the denominator of y, we have 1 minus y square over x square over y over x, right? So now we can see that this function f of x comma y can be written as 1 minus y over x square, and here we have y over x, right? So now we can see that this is a function which is in the form that is y over x. So we can write this function as, say, phi of y over x. So this is a homogeneous function of degree 0, and this function is completely expressible in terms of y over x. So whenever we come across with these type of functions where we have the function in the form of y over x, then we have the differential homogeneous differential equation of the first type, right? So what we will do in these cases, we'll take y over x as some parameter, say v, right? And v is a function of x. So v is a function of x. So we'll take y is equal to vx, and if we differentiate both sides, we'll get dy over dx. And here we have the product rule. So the first function, derivative of x with respect to x, that is 1, then x, and then dv over dx. So we'll take dy over dx is equal to v plus x times dv over dx. So now we'll return to this expression. So we have dy over dx, and here this expression is equal to f of x comma y, which is 1 minus y over x square, and here we have y over x, right? So now we can take v is equal to y over x. So dy over dx is v plus x dv over dx. So dy over dx is replaced by v plus x dv over dx, and here we have 1 minus v square, y over x is v, and here we have v, right? So now we have a differential equation in terms of x and v, and remember v is a function of x. So let us rearrange the terms here. So we have x dv over dx is equal to 1 minus v square over v minus v. So taking this v to this side, so now we have x dv over dx is equal to 1 minus v square minus, here multiplying this v by v, we have v square, here we have v. So we have 1 minus 2v square over v, right? So now we have an equation, x dv over dx is equal to 1 minus 2v square over v. Now here we have a variable separable form. So we can separate the variables, that is v on one side and x on another side. So now separating the variables here, we can write v. Here we have v over 1 minus 2v square dv is equal to a dx over x, right? So what we have done here, we have taken all the v's to the left hand side and all the x to the right hand side. So now let us integrate both sides. So here we have a constant of integration c. So now here we have a simple integration and we can solve it by method of substitution. So let us take t is equal to 1 minus 2v square, and here we have dt over dv is equal to minus 4v, and we can now write dt over minus 4 is equal to v dv. So v dv can be replaced by dt over minus 4. Here we have simply t, and here we have the integral 1 over x dx is log of x, right? So here we are will prefer the notation log, that is log in place of ln, right? So we can also write it here ln x. So here we have c, and now we have minus 1 over 4 integral dt over t, and this is log x plus c. So this is minus 1 over 4 integral 1 over t dt is simply log of t. This is log of x plus c, right? So now what we will do, let us multiply this equation throughout by 4, right, or minus 4. So what we will get here, here we are simply left with log of t. Here we have minus 4 log of x, and here we have minus 4 times c, right? So now taking this term to this side, we have log of t plus 4 log of x, and here we have a minus 4 times c. So we can take this 4 to the power of x by using the properties of log. So we have log of t plus log of x raised to 4, and here we have minus 4c. So now using again the properties of log, we have log m plus log n is equal to log of m times n. So here m is t, n is x raised to 4. So we have log of t times x raised to 4 is equal to minus 4c, right? So now let us take the exponential of both the sides. So we have e raised to log of t times x raised to 4 is equal to e raised to minus 4 times c. So here we have e raised to log t times x raised to 4. So using e raised to log of p is equal to p. This is an important relation. So here p is t times x raised to 4. So we have t times x raised to 4 is equal to say k, right? So here replacing this constant e raised to minus 4c by k, k is some other constant, right? Now replacing t by 1 minus 2v square, and here we have x raised to 4, and here we have k. So now replacing v by y over x, right? So we have 1 minus 2 y square over x square, and here we have x raised to 4 is equal to k, and now multiplying these two terms by x raised to 4, we have x raised to 4 minus 2y square x square, right? And here we have k. So we can also write this solution as x square. Taking x square common, we have x square minus 2y square is equal to k, where k is some constant or the constant of integration. So where this is the general solution of this differential equation. So now to get the value of the constant of integration k, we'll make use of the boundary conditions. So the conditions are y of 1 is equal to 1, right? So when x is, this is the value of x. So when x is 1, y is 1. This is the value of y. So taking these values in this equation, we have 1 square. Then we have 1 square minus 2 times 1 square is equal to k. So this is 1 times 1 minus 2 is equal to k. So this is k is equal to negative 1, right? So the constant of integration k is equal to minus 1. So taking k is equal to minus 1 in this equation, will get the particular solution of the given differential equation. So we have x square, we have x square minus 2y square, here we have minus 1, right? So this is the particular solution of this differential equation when the boundary conditions are x is equal to 1, y is equal to 1, and this is the general solution, right? Now let us consider the second homogeneous differential equation.